So in the lab this week, what we're going to do is we are going to determine the molar mass of an unknown solid that we're going to be given. So we have to experimentally determine this. Now if we go back to what the molar mass is and the units of it, it's the grams per mole ratio for a substance. So if we're going to calculate the molar mass or determine the molar mass experimentally, that means we need to know the relationship between the number of moles of something and the mass of it. Well, experimentally, that part's easy, right? You just take a solid, you put it on a balance, and you get the mass. Experimentally, the number of moles, okay, is not so easy. We can't just take it and put it on a mole balance, and that mole balance tells us the number of moles, right? That's not something that we can do, right? We can just weigh out the mass of a solid. So we need to figure out how can we actually identify the number of moles of something. Well, we're going to see that there's a relationship between the number of moles, right, which is dealing with the number of particles, and the freezing point of a solution. Okay, so in our courses, we've been talking about colligative properties. One of those colligative properties is freezing point depression. Okay, so if we're looking at the freezing point depression of a solution, okay, we would see, well, the change in our freezing point is equal to the freezing point depression constant times the molality of our solution. Okay. Well, this is a constant based upon our solvent. So whether our solvent is water, hexane, in lab this week it's going to be cyclohexane. And then the freezing point depression temperature change is just simply, it's going to be dealing with the freezing point of the pure solvent minus the freezing point of the solution. Okay, so it's just the difference, right, that we would have as we're looking at our freezing point. Okay, so the molality of the solution is what could affect how much our freezing point changes. So if experimentally, let's go ahead and say we have it set up where what we're going to do, first we go ahead and we need to know what our freezing point is for the pure solution, or pure solvent, excuse me. So we could go ahead and measure the freezing point of our pure solvent. That's something experimentally we could do. We could look at and measure the temperature that it freezes at. Now if we go back to thinking about how are we going to identify that temperature that something freezes, if we go back to kind of our cooling curve relationships, right? And we learned this a lot in lecture. If we look at the temperature that something has and the amount of heat that's released, because we're dealing with a cooling curve, we let something cool down, cool down, cool down. At some point, it remains at a constant temperature, and then again begins to cool again. Well, if we go back and remember, why does it stay at a constant temperature? Well, it stays at a constant temperature because now it's undergoing a phase change, right? And so the phase change that we're going to measure here is we're going to be looking at going from a liquid to a solid, right? The temperature that it freezes at. It's going to remain at a constant temperature for our pure solvent. Once we do that, we can see, well, that's going to tell us our freezing point. So experimentally, this is something that we can observe fairly easily. We need to actually get our baseline, right? We got to first figure out what temperature does our solvent actually freeze at if it's just our solvent, okay? Then what we're going to do is we can go ahead and we can measure the freezing point of our solution. So we can dissolve some amount of our solid solute, and we're going to know how much of our solvent we have. And we could go ahead and measure the freezing point. Okay. Now note this freezing point of our solvent, okay, that does not depend on the amount of that solvent. If you have 5 grams of cyclohexane or 75 grams of cyclohexane, it's going to freeze at the same temperature. Okay, it doesn't change. Whereas if we're dealing with our solution, we're going to see that the relative amounts of our solvent and our solute are going to affect it, right? The higher the concentration, the greater it's going to affect our freezing point depression. So if we add a specific amount, right? A specific amount of our solute to a specific mass of our solvent, that gives us a distinct ratio, okay? Well, when we're adding this, right, that's going to be the grams. That's the amount of our solute, right? And we can go ahead and get to the grams of our solvent, right? Those are things, again, we said that's easy. Something easy to actually measure out, we just put it on a balance, right? Well, again, we can measure the freezing point. Well, then what we're going to be able to do is we're going to be able to quantify that freezing point depression, and we know the constant, and so what we're going to be able to do is we're going to be able to calculate our molality, okay? So from this, we're going to be able to calculate the molality of our solution, okay? Once we calculate the molality of our solution, what we're going to be able to do is we see, well, that is moles of solute per kilogram of solvent. Well, this is great for us, right? Once we've calculated molality, we'll have the kilograms of our solvent, right? Because we'll see that we've gone ahead and we weighed that out. We know how much of the cyclohexane we have as our solvent. We're going to be able to actually calculate the moles of our solute. So now by measuring the freezing point change, we're going to figure out the moles of our solute that relate to a specific mass. Then what we're going to be able to do is we can go ahead and we can calculate the molar mass of our solute, right? We don't know what the solute is, but we do know that it dissolves in cyclohexane. And we will have a specific amount of our solute that we weigh out. And then we would see, we're going to be able to calculate the number of moles of our solute. And then once we've done that, we now have the ratio between the mass and the number of moles of a substance, which in this case is our solute. And we've arrived at our goal, which is identifying the molar mass of our unknown. Okay. So in lab, we're going to see that this is kind of the big picture we want to do. We need to measure the freezing point of our solvent. We again are going to add some specific amount of our solute, look at how it affects our freezing point. From that, we can get our freezing point change, calculate our molality. Once we get our molality, we're going to be able to get to the ratio of the grams of solute per moles of solute. Okay. So in lab, your individual instructor is going to kind of give you some guidance in how we're going to do this, what are some special hints that we can think about, but it's this kind of big picture of just looking at measuring freezing points. It's going to get us the ability to identify the molar mass of our unknown. So I hope this gives you a good idea of what we're going to do. Look forward to working through this lab with you in the upcoming week.